Alright, so this video, the goal is to show, prove, I guess, the product rule, the quotient rule, and the chain rule for derivatives. So we're looking at section 3.3b in our text, and this is, just looking at product rule, quotient rule, and chain rule. So let's get started. So in order to prove the product rule, we need to first just figure out what we're dealing with. So we're looking at the function f times the function g, and we're trying to take the derivative of that. So what does that mean in terms of our definition of the derivative? Well, that means that we're looking at a limit as h approaches 0 of f of x plus h times g of x plus h minus f of x times g of x, all divided by h, right? This is our derivative, definition of our derivative, and we're just using this product. Okay, well, that looks like it's kind of hard to work with, but one of the things in our tool bag of mathematics for doing stuff that we want to do is adding 0. So we're going to use the strategy of add 0. But the 0 that we're going to add is actually very special. We are going to add, what are we going to add? F of x times g of x plus h, again, but flip the sign, so g of x plus h. There, see, that's 0, right? That equals 0. So if we add that in here in our numerator, then what do we get? Equals limit h approaches 0 of f of x plus h times g of x plus h minus f of x times g of x plus h plus f of x times g of x plus h minus f of x times g of x. And this is all over h. Where did these all come from? Well, that's right there, and this is right there, and then the rest of it is just 0. All of that's 0. Okay, so let's just take away some of those very big highlights. Sorry. Okay, so what do we have here? Well, we have this limit as h approaches 0 of, and what can we do with these first two terms? We have g of x plus h and g of x plus h. So we can factor out g of x plus h from everything in those first two terms, f of x plus h minus f of x. And this is all over h. And am I allowed to break this up so that I deal with these separately? I can take these two and just this whole numerator I can split up into multiple parts. I just want to deal with 2 parts. And let's see. So what do we do now? Well, we have, this is f of x right there. Ooh, that's really thick. So we have f of x right there, and we have f of x right there, so can't we factor that out as well? F of x times g of x plus h minus g of x, and all of that is over h. Lovely. So I'm looking at a limit of 2 different fractions. So how can we deal with this using our understanding of derivatives? Well, if we're looking at this limit and we have all of this, can't we take this second part, this f of x plus h minus f of x, and just divide that part by h, and so just leave the g of x plus h alone? So then we get what? Limit as h approaches 0 of g of x plus h times, can't we do something else? When we have a limit, can't we look at the limit of the product? Yeah, because limits are just numbers, right? So we have limit as h approaches 0 of what was inside here. I'll just switch to the lava f of x plus h minus f of x all over h, right? That's valid. Plus, and then I can also take my limit of this part separately. So then is this. This is limit as h approaches 0 of f of x times the limit as h approaches 0 of g of x plus h minus g of x all over h. Well, would you look at that? This part looks very familiar. What does that look like? F prime. And this part also looks very familiar. What is that? This is our definition of our derivative, g prime. When we plug in h goes to 0, what do we get there? G of, not 0, g of x plus h, which goes to 0, so it's just g of x, times f prime of x, plus the limit as h approaches 0 of just f of x, that's just f of x, that doesn't change at all. And here we have our definition of our derivative, g prime of x. So when we're looking at our derivative of a product of two functions, f times g, derivative of that, the derivative of this product, we get g times f prime plus f times g prime. Alright, so the quotient rule is actually just pretty much very similar to the product rule, except there's a little bit of a tricky part. So let's just get started. So what do we have? We have the limit. Oh, what are we looking at? We're looking at f over g and the derivative of this quotient of two functions. So we're looking at f over g, and these are two functions, and we're looking at its derivative. So let's look at this. Limit as h approaches 0 of f of x plus h all over g of x plus h minus f of x all over g of x all divided by h. Interesting, interesting. So what should we do from here? Well, I think we need to add 0 again. But what could be useful in this situation? Well, I think that we might need to handle this with a little bit of algebra, kind of like jujitsu stuff. So, limit as h approaches 0 of, and I'm going to factor out this reciprocal, because division is just the same as multiplying by the reciprocal, right? So, if we have, this is f of x plus h all over g of x plus h minus f of x over g of x. Right? That's valid. So maybe I need to get a common denominator. So what do we get? Limit as h approaches 0 of 1 over h. F of x plus h times g of x minus f of x times g of x plus h. And this is for my common denominator of g of x plus h times g of x. Okay. Well, that is like okay, but how can I make this a little bit easier to work with? Well, I think I need to add 0 again. But the 0 that I want to use, I think this time, because we have like all of the small changes mixed up together with our not small changes. So what if we just have g of x times f of x? Or should we swap the order around? F of x times g of x? It doesn't matter too much, right? Because these are still it's the product, and product is multiplication is commutative, so that's nice. So let's see. We get limit as h approaches 0 of 1 over h times f of x plus h times g of x. And I'm going to do this, oh, sorry. We're going to do this minus and this plus, like this. Okay. So we should subtract g of x times f of x, and then add in f of x times g of x, and then minus, oh boy, what did we have? F of x times g of x plus h. And all of this is divided by g of x plus h times g of x. Close that bracket up. So this is the same because the only thing I did was take this 0 and add it in right there. Okay, so from here, can I do any fancy grouping? I think so. I think so. So let's see. What should we do? We get this is equal to limit as h approaches 0 of 1 over h, and then well, actually, I think I might want to deal with this 1 over h as the denominator for what I'm working with on this side. Because over here, we have some like changes in our h's, and changes in our x values, our inputs. And so I want to swap my denominators. So I'm going to factor out the g of x plus h times g of x. And instead I'm going to put this all over h. This, what is this? Well, I can factor out a g of x times f of x plus h minus f of x. Oh, do you see what we have here? Oh, wow, that's so exciting. Look at that. That's the derivative. Okay, and then plus, let me see, f of x times, or should I make this minus? If I factor out a negative f of x, then what do I get? I get negative g of x plus g of x plus h, and this is all still over this h. So now, what do I get when I evaluate this first part with my limit? I get 1 over g squared of x, right? When I evaluate my limit here, well, that doesn't do anything. I just get g of x. And actually, with this, I also just get f of x. But then in here, with this orange part, well, that's our derivative of f. And over here in the blue, with this h, we have definition of our derivative of g. So what we're left with is actually, I'm going to put a bracket there, so we got g of x times f prime of x minus f of x times g prime of x. And yeah, that seems pretty good. We might want to write that instead as g of x f prime of x minus f of x g prime of x all over g of x squared. And this is our derivative of f over g, that quotient. This one has a I guess it's like a jingle or something. So if we have high is f, and then low is g, and then we have a notation of like d dx of like f of x. This is equal to like the derivative, right? So another way of saying this is like that this is df. You can say df. So, or to remember it, we just go with like low and high. So low. Oh wait, let me use this. Low d high minus high d low over denominator squared we go. Again, low d high minus high d low over denominator squared we go. And if you flip it, it's wrong. So that would be high d low minus low d high over denominator squared, you die. And I think Mr. Stein's website has a recording of Mr. Paul singing this with, because Mr. Paul used to teach at Blair. He's in law school now, but he was part of intonation when he was a student, and so there's a recording of his intonation group singing the quotient rule song. So low d high minus high d low over denominator squared, we go. Don't do the other one. That's wrong. Okay. What about the chain rule? With the chain rule, we're actually looking at two functions composed in one another, and then we're taking our derivative of that. How can we handle this? Well, okay, so if we're looking at our composed functions, and maybe we need to use this definition, our alternate definition of our derivative, where we're looking at x approaching some c value, not an h or a change in x going to 0. So pause the video and think, how could you maybe prove or figure out, not even prove, just figure out what this derivative is. Okay, so try to pause the video and think about it, and then we'll see how we get. So, well, let's look at this. So if we're looking at our derivative, and let's just for good measure, let's call this f of g of x. Instead of it x, let's look at it at c. So some c value, and let's call this like a different function, just so we don't have to write it as much. So h prime is h is f of g of x. Okay, so then h of x. So then when we're looking at our derivative of h at c, then we're looking at this composed function. Okay, so our derivative there is going to be limit as x approaches c of f of g of x minus f of g of c all over x minus c. Now, with the other two rules, we were adding 0. That was our tool bag thing to do. But for this one, I think we need to multiply by 1. Now, what kind of 1 do we want to use? Well, I think we should probably multiply by a 1 that has our g's handled pretty nicely. So what if we multiplied by g of x minus g of c in our numerator and our denominator? Whoa. Okay. Well, this is 1, right? So we haven't changed the value of this limit. But if we do this, and we know that multiplication is commutative, right? Then we can look at this limit as x approaches c of f of g of x minus f of g of c all over g of x minus g of c times g of x minus g of c all over x minus c. Do you see how I just swapped these two denominators? Just change them. Well, that's totally acceptable, right? So then from there, what should we do? Well, looking at this, we actually do have an understanding of what this means, right? Because we're looking at the small change in our x value we're looking at as x approaches this c value, and that's our nifty input for both of these. We're just looking at this composed function. So the composition of these functions actually doesn't worry us too much, because we're just looking at f prime evaluated at g of c. That's what this first part is when we take our limit. And for the second part, if we're just sneak in this limit notation as x approaches c, so that we multiply properly. So we can have all of that together. Okay, so then we have all of that together. And what is that? Well, that's just g prime at c. So we're looking at g prime at c. And there you go. F of g of x if we're looking at our derivative there, this is f prime of g at that x value multiplied by g prime evaluated at that x value. So the chain rule is just taking this composition of these functions and we're just making a chain. So if you had like h of g of f of x, then chain rule, if we're looking at our derivative of all of this, then we would just get h prime of g of f of x times, and then the next link in the chain is g prime of f of x times, and then to finish out our chain, f prime of x, and boom, there you go. It's a really bad circle, I'm sorry. But the chain rule, using composition of functions, we can actually take our derivative. So if we are very careful with that, that can definitely make our lives easier. Alright, so try these two problems, and then I'll see how you do. So with A, that's a G. With A, I just want to do a Y prime. Okay, so this is actually, we're looking at a product, right? This is F, and this is G. So first times the derivative of the second, so that's what? X to the, I'm going to flip that into a 2/3 power, times the derivative of the second, which is G, so that's 2 minus power rule 2x, plus the derivative of this one, which is what? 2/3 x to the negative 1/3 power, because 2/3 minus 1, negative 1/3, cool, times that second function g, 2x minus x squared. What about b? Can you try b? This is also a product rule. Oh, but I guess this is an f, so maybe we should call this h times g. So we get h times g prime plus h prime g. What do we get? F prime of x is 6x cubed minus x times, and what's our derivative here? Just negative 20. Plus, what's h prime? 18, because 6 times 3 there, and then we get, what, x squared minus 1, because of the power rule. Okay, let's just simplify that, because why not? Negative 120 x cubed plus 20x plus 18x squared minus 1. Okay, cool. Is there a greatest common factor in this? Not really. Do I feel like factoring that more? Not really. Alright. Here we go. How about these? Can you try these? So what's, from A, what's W prime at Z? Well, this is a quotient rule, so that's low D high, so 2 minus Z, derivative of the numerator, which is just a 3, minus high D low, which is 3Z plus 9, times the derivative of the denominator, which is just, oh, it's just negative 1, so I'm just going to throw a plus right there. All over denominator squared we go. And for good measure, let's just simplify that out. What will we get? Like negative 3z plus 6 plus 3z plus 9, and pew pew, those cancel. We get 2 minus z, quantity squared in the denominator, and so we get what? This is like 15 over 2 minus z squared. Not always necessary to simplify. In fact, on your AP exam, you're encouraged not to simplify, but in order to communicate well, I think that it is best practice to practice simplifying. Unless I tell you to just leave it as it is. Yeah, simplifying is good. It's good for you. Builds character. Alright, so we go about B. B is also a quotient rule. So h prime of x, low d high, so that's what? X squared minus 2 times the derivative of the numerator, and this numerator is 4 times x to the 1/2 power. I'm just thinking about that. So then that's nice, because then we end up with like a 2x to the negative 1/2. minus high, which is 4x to the 1/2, d low, which is 2x, all over x squared minus 2 squared. Wow. Well, actually, that feels like a lot of effort. Maybe we should simplify that one. It's grossly, I don't know. This video's getting long. Okay, C and D, can you figure those out? And I'll put a little quiz question. What are C? What's the value of f prime? And what is the value of y prime with respect to w? Okay, so f prime of x for C. That's not too bad because that's 4 times x to the negative 6, so that's just negative 24, the power rule, times x to the negative 7. And D, well, that's just, that's not even like a ton of effort. It's just 6/5 w to the 5th, and that's it. Suppose that the amount of air in a balloon at any time t is given by this. Determine if the balloon is being filled with air or being drained of air at time t equals 8. So what does this mean? This means that the rate of change needs to be positive if it's being filled with air, right? The rate of change of the volume of the balloon needs to be positive if the balloon is being filled with air, or if the balloon is shrinking, then the rate of change of the volume needs to be negative. So how would you figure that out? Pause the video, try to answer. All right, so we're actually looking at our derivative, right? V prime of t. And this is a quotient rule, because this is f over g, and we're looking at our derivative. So take the derivative of our quotient, low, d high, which is 2t to the negative 2/3, minus high, which is t to the 1/3, d low, which is just a 4, over denominator squared. We go, okay, cool. V prime at 8. How do we figure that out? Well, let's just plug it in. Wow, it seems like a lot of effort. So let's just talk through it. So if we have 4 times t plus 1, and we're plugging in 8 for t, well, that's going to be a positive number, and that's going to be, well, I guess since we have a subtraction, we should probably do it. What is that? 33 times 2 times t to the negative 2/3 power, which is, what, just 1 over 4, minus 6 times 2 times 4, okay, and then this is all over, what, 33 squared, which is, since it's squared, it's always going to be positive, so non-negative, it's an r plus. The non-negative reals. 33 times 2 over 4 is something like, I don't know, it's like 8-ish times 2-ish, which is like 16-ish. 16-ish minus that, which is negative like 48. So this is going to be less than 0. So the balloon is being drained of air. So we could write this as V prime of 8 is less than 0 at therefore the balloon is being drained of air. Okay. If there's 3 functions for a product rule, what would happen? Well, we could group these, right? We could group these as some function, let's call it j of x. So then it would be just j prime h plus h prime j. But then j prime is going to be f times g prime, which is f prime g plus f g prime. So then j prime, this j prime is going to be this. So f prime g plus f g prime all times h plus h prime, and then j, which is g f, and I just changed the order of that entirely, but that's okay. So then we get f prime, that's an f. We get a f prime g h plus f g prime h plus f g h prime. And this is nice. You just go through, you parse through the derivatives when you have a product of multiple things. It's not too bad. All right. So this is how we are going to end this video. You need to show one of these. You need to demonstrate it. Make a write-up of yourself, of your own making. Write up the derivative of one of these trig functions, and you can show it using probably some of the rules that we learned today. Okay? So that is an assignment for you until we meet again.